Martin Jackson, who's going to talk about, as you can see, words that are difficult to say, allochthonous. Martin, the floor is yours.
Well, I really got the hot seat this afternoon. Not only am I standing in, or sort of standing in, for the senior medalist, but I'm also the only thing keeping you from the drinks reception. What we're looking at here is the top of a salt dome here. It's the most spectacular and beautiful mountainous salt in the world in southern Iran. And it's the top of a diaper that is several kilometers deep, and from the crest, just out of sight, are two salt glaciers that flow just like ice glaciers today. Those are probably the most spectacular, but not the biggest, variety of allochthonous salt, which is the subject of my talk today. So first off, what is allochthonous salt? Well, it's salt that's come up from depth down here in what we call the source layer, it goes by another long name, autochthonous, and has risen up as sediments accumulated around it and then spread out over the top. So what we have is a situation that defies the normal law of superposition, and that is we're having old salt resting on younger sediments. And that is the thing that qualifies it to be allochthonous. The geometry and evolution of allochthonous salt is very important for applied reasons, especially in exploration, oil exploration, but even occasionally in mineral exploration. It's important for two reasons. First off, if the exploration target is down here in the subsalt region, then the salt above it can act as an impermeable seal to seal the trap for the hydrocarbons. And secondly, sort of what is a little less well known is that they act to distort seismic waves, which is the principal tool for investigating subsalt regions. And a bit like if you hold up a glass that's a sort of lumpy piece of glass to your eye, it will distort everything you see through it. Well, this is looking downwards for the seismic waves, that distorts the waves. So they're trying to drill a particular spot, which they can now do with very high precision. And they could miss the spot entirely because they haven't predicted seismically accurately where it is. And to do that, you have to know the exact geometric shape, and preferably how it evolved that way, of the overlying salt to interpret what's below. So the applied benefits are huge. I'm going to talk this afternoon not about applied geology, despite the William Smith Medal, but about the pure geology side of things, because I think this makes for a more interesting talk. So first off, it's quite common. Of all these red blotches that you see here, are about 140 salt basins around the world that are known to have salt tectonics. In other words, a considerable amount of deformation involving salt and the sediments around it. And of those, 35 basins have allochthonous salt. So quite a large proportion. Well, why not all of them? Well, you need special conditions to form allochthonous salt. Two are really essential, and one is certainly helpful and useful. First off, you need an adequate salt supply in the source layer. That's this layer down here. This has to be thick enough in order to grow a large salt structure. And if I don't point it out in nearly all these slides, the diagrams, the salt is going to be red. So you need a generous supply of salt at depth. You also need a great thickness of sediments above to press down on the salt and drive it up to a more stable position near the surface because it's buoyant. So that'll help to make a big diaper. And then the third thing shown by the green arrows is a displacement loading. This is purely a gravitational load. Displacement load is like a vice that closes in on the diaper, squeezes it together, and forces the salt up and out at the surface. So those three things are really helpful to make allochthonous salt. So what do they look like? Well, this is the same structure that I showed in the opening slide. Kuy-Namak, or mountain of salt in Persian. It sits near the Gulf Coast of Iran and Arabia, and a few kilometers inland, and rises from a long anticline, which you can see nicely exposed as a whaleback structure here, plunging off in this direction. It has a summit here about 1,400 meters above the surrounding plains, which are younger sediments filling in the synclines. The terminus of it, the end of the salt glacier, is down here. So from ground level, this would be the summit, and this would be the salt glacier thinning off in the distance, gradually getting thinner by dissolution. The combined salt glaciers, this one going to the north and another one you can't see very well, are 10 kilometers long. So they're pretty sizable, but that particular size is dwarfed by what you'd find in the subsurface. So we now know a little bit about the rates at which these things come up. In the old days, because of the rock mechanics was not very kind to salt, there was a widespread belief that you had to heat salt up to make it flow. So the mental picture that people had was that these salt glaciers would come pouring out the ground some eons ago, red hot, and therefore mobile. Now we know that they flow actually almost as fast as ice glaciers, and like ice glaciers, they surge and they have periods of more stable growth. And we know this mostly by the work of Chris Talbot and a whole succession of students of his since the late 1970s. They first published their work in Science, and what this showed was that the salt glaciers are moving under extremely low differential stresses down a very gradual slope, and that they could advance at the rates of meters per year. And how they knew this was that Chris and his colleagues would build a survey station on the edge of the salt glacier, and then survey in several cairns that were built on the moving salt glacier, and then come back months and years later and keep remeasuring them. And to give you an idea of what the sort of landscape looks like, this is a 180-degree panorama looking up back at the summit, and then the salt glacier is flowing past us, and there's the dissolving snout of the glacier. And inside each of these red circles is one or two humans for scale. Well, this flows pretty rapidly by geological standards, but it cannot flow forever. There's a finite quantity of salt down there, and once you run out, no matter how much you squeeze it, you run out of the raw material to make more. So what Talbot and his colleagues have put together is a synthesis of the life cycle of what one of these would be. It starts off with the top of a diaper. Now remember, this is only the top, and the bottom of it would be several kilometers down. So it emerges as a simple topographic dome. This is what that would look like, this one in Far Eastern Iran. Basically just a plug of viscous salt oozing out of the ground. As it matures, that salt dome rises and rises until it cannot support its own weight, and it just begins to spread sideways. And this is the so-called salt fountain. And it's just like a slow-moving viscous fountain of any fluid, magma or even water. The vent here is where it's coming up, and that is overlain by a dynamic bulge. This is a bulge elevated into the air by the pressure of moving salt. So as an example, here's a beautiful one. It looks like a fried egg coming out the ground between the mountain ranges in Iran. And this is the dynamic bulge. That would be the yolk in the fried egg. And so that tells us the vent of this structure is right here in the middle, and it's just spreading outwards in all directions from there. And you note we had these low-bait flow fronts, just like the talk we heard on avalanching. So that continues as long as it's well supplied with salt. Again, helped by the fact this is in a fold belt and is being squeezed like a concertina, so that the salt is being squeezed up to the surface. But eventually we run out of salt at depth, or we squeeze the vent shut, and it evolves into what's called a salt droplet in fluid mechanics. that means that this crestal dynamic bulge begins to subside and just flattens out, and it forms just like a droplet on a freshly waxed car. It's spread out as far as it can. Meanwhile, it's still under continual dissolution from rainfall. So the salt is now no longer replenished, so it just starts to shrink, and it ends up with what's picturesquely called a salt ruin. And this would be an example of it. The original vent that supplied the diaper is often marked by a crater wall, and inside the crater it's choked with insoluble debris. These are sedimentary rocks, metamorphic rocks, igneous rocks that are all much the same age as the salt itself. And they came up with the salt dissolved and left this melange, this mess of particles ranging from dust size to several kilometers in size. That gives you an idea of the carrying power of the salt. Well, let's talk a little bit about how these features advance. Here's a seismic section from the Gulf of Mexico, and it shows a buried salt sheet. But I want you to imagine a time before the sedimentary roof was deposited, and it was still flowing at the surface. And that would be a sort of two-stage evolution that we see here. As the salt is advancing forward by extruding, sediments are building up or are grading in front of it, because this is an active sedimentary basin. And where the sediments meet the... This is dying. Do we have a backup? Thank you. Where the sediments meet the salt sheet, they trend back like this and hit the contact of the salt sheet. This is what we call a basal cutoff. That's a very important stratigraphic marker because it tells us that at the time of this sediment, whatever its age was, the front of the salt sheet was here, then it advanced to this point, at this age of sediment, and so on. So for instance, we have a cutoff number 2 here, marked by that layer there. Later on in time, we can find that cutoff here, and if we've got the age of that layer there, we know that was where the front of the salt was at that stage. So we can reconstruct the spreading history of this feature. And you can also do it in 3 dimensions, because you can just map these cutoffs in map view like this, and that gives you the full 3D evolution of the structure. So that's what happens if the sediments have not yet buried the structure. Once they have buried it and it has a sedimentary roof, then it cannot advance by extrusion anymore. It's got this lid on it. And then the only way it can advance is by having the salt sheet and its roof, like a snail in its shell, moving forward together. And the roof acts as a kind of protection from dissolution. So it's actually a very, very stable, long-lived way of advancing. So to do that, the roof has to break at its front in a number of different ways. All of them are thrusts. So in diagrammatic form, the 2 main types are the imbricate wedge, which looks like this. Here's a seismic example. And what's happening is the salt sheet is moving from left to right, and it's bulldozing up the seafloor ahead of it and stacking them up like a snowplow would. The other type, which is more subtle but harder to see, but more important, is the roof edge thrust. So that would be this one here that connects down the base of the salt. So this places older sediment on younger sediment, like all thrusts do. For example, this salt sheet has advanced 5 kilometers in the last 2 million years. This gives you an idea of the rate of advance. And we can tell that by looking at the age of this sediment here, finding the equivalent age of sediment up here, and the lateral offset is the amount it's advanced. So what happens when these things have advanced and they meet a neighbor? Well, then you have 2 salt sheets, 2 allochthonous sheets, combining together and coalescing to form what we call a salt canopy. The first canopy was described in the Great Kavir in Iran. This is the largest salt desert in the world, and it's in north-central Iran. The diapers there are about 50 of them altogether, but 12 of them, which I'll outline here, have joined together, just as if you were making pancakes in a frying pan, and the batter just spreads and joins. The outcrop has two things that were extremely fortuitous that enable these to be discovered. The first is that the erosion level in this desert was at just the right level, not too shallow and not too deep, either of which would have missed the canopy entirely. The second fortuitous thing is that the diapers are made up of salt of two ages, this pink Eocene and the darker colored Miocene, and they're very easy to tell apart in map view. So they can be easily mapped out, and you can see they define a cellular structure. So even when the diapers are joined together, all the pancakes have merged, we can still see how many pancakes were there by the ring-like cellular structure. So that was the first canopy described, but it's an absolute dwarf compared to what we know nowadays from the Gulf of Mexico. To give you an idea of scale, I've dropped London and Glasgow on here in offshore Gulf of Mexico. So what we see is the Texas, Louisiana, the shelf looking smooth and boring, to a structural geologist anyway. And then this dimpled slope, dimpled by little mini basins that are sinking into salt. And the salt is very, very thinly veneered in places, and it's advancing by means of this 6B escarpment over the abyssal plain. So everything is driven by gravity, spreading down slope and oozing out over the plain here. The 6B escarpment runs for a sinuous length of over 1,000 kilometers through the northern Gulf of Mexico. It's the largest near-surface structure, salt structure on Earth. Its average height is about 800 meters, but it gets up to about 1,400 meters. And this is the viscous flow front of mostly salt, but with this veneer of sediment. So I'm going to show a couple of model pictures from my colleague Tim Dooley in Austin. And because of this modeling, we can now interpret, I think, seismic pictures with much more accuracy or imagination than would otherwise have been possible. So on the left-hand side, we can see a seismic map view of two diapers. This is one here, this is another here. The yellowish areas are areas that have been inflated where the salt has pushed the sediments up. The blue areas, like a giant thumbprint, are where the sedimentary mini basins are sinking down into it. And you'll notice that we have what we call a cusp here, a sharp change in direction of the edge of the salt sheet, and that lines up with a trench here, and that goes around to a cusp the other side. And there's some weird striations on here. If we look at the experiment here, which is an overhead view of a sandbox and silicone experiment done by Tim, we can now interpret what these features mean. The purple lines are salt sutures, in other words, the boundaries between one diaper and the next. Back to the pancake metaphor, if you've got a dollop, spoonful here and a spoonful there, where they meet is the suture. So that's shown by a purple line. And you'll notice most of them are bowed asymmetrically into one diaper, not the other. That's because the more active one is flowing into and spreading into the less active one. So we can now go back to the seismic and say this sheet here is spreading, overriding its southern neighbor there. The spreading direction is shown by the red arrows here. The other thing we see are these extensional lineaments. This is where the pancake, if you like, is spreading wider and cracking open its roof. So these are extensional lineaments, and they're radial, going in the direction of flow. And again, we see them on the seismic image of the top of the salt as well. So what do they look like in cross-section? Well, on the left-hand side are two diagrammatic block diagrams. On the right-hand side, two seismic sections. At an early stage, this diaper or salt sheet here is overriding its neighbor here, in the same way that salt sheet A here is beginning to override salt sheet B. So this is the vigorously spreading one. This is the purple line you've just seen in the suture. And you'll notice that it's trapping sediment between the two sheets, and that sediment is the former roof of salt sheet B. This is overriding it like a tank tread over the top of it. When it becomes a little more mature and salt sheet A is really rolled completely over into salt sheet B, those trapped sediments get strung out and broken up into little inclusions. And we can see those seismically. There's one here, 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 and here. And together we can draw a line through them, and that defines the suture, or the boundary between the two different salt sheets. You don't see the feeder part, which is the vertical one, in this view, but it is there. So not all of us have had the experience of this bedroom scene, but even those that haven't could appreciate the physics that's involved here. What we have is a heavy object sinking down into the fluid, and that displaces fluid from underneath it and pushes up the lighter object. And we see the same thing in this model here. The heavy load is the thick sediment here, and that's pushing down on the diaper, the yellow one marked sheet A, and that's displacing it sideways into sheet B, because sheet B is overlain by a much thinner overburden. So you've got the light load, it inflates, a dense load, thick load, it deflates. And that redistributes or recycles salt around the canopy. There are three main ways in which you can recycle salt within the canopy, and between them, those three ways, which are all end members, they're seldom 100% pure ones in nature, but between them, they recycle it to make the most complex type of salt structures known, which is why I saved them up till the end. This one is called the Rojo system, and essentially what it is, it forms on the continental slope, so there's a gravity drive forcing things down slope. A salt sheet comes out of the surface, it then gets loaded with wedges of sediment behind, and that begins to then break up by extensional faults, and you can then get a vast number of, in this case about 60 kilometers of extension in a very short area that is stretching the sheet as it flows down the slope. And we recognize it by the fact that strata thicken and dip landward, which is to the left, as they rotate on these faults. What they leave behind is a vanished salt called a salt weld. And you can see it started off this thick up here, and it ends up that thick. So here's a salt weld going all the way along here, and then we reach the thicker part of the structure. The other type, the second type, which superficially looks the same, but is distinguished from it because here the strata are thickening and dipping seaward, not landward as in the previous example. There is no extension involved here, or a negligible amount. Instead, like a giant sort of squeegee, the sediments are moving across the salt sheet, prograding and expelling the salt out ahead of it, recycling the salt that was in these more proximal regions, sending it seaward to the distal parts, and driving new diapers up ahead of it. The third type is called a salt stock canopy, and this is probably the most complex in 3 dimensions. If you can envisage, we have a whole series of diapers that widen upwards through time. They're circular in map view, so they're called salt stocks. They're all growing together, they're all spreading together. Little mini basins are beginning to sink down into them because that's a place that is where material can be moved aside as they sink, And so the mini basins sink down, the salt underneath them is displaced up sideways from each diaper, and there they merge to form a canopy. So now what you've done is to replace what used to be salt here with a mini basin and displaced all the salt on either side of it to between the mini basins. So in map view, it would look like this. Here are the mini basins where the diapers used to be, these egg-shaped green bodies, and then the salt displaced out of there to form this kind of polygonal network of second generation diapers. When salt moves laterally, it can carry mini basins for tens of kilometers. Diagrammatically, you can imagine we have a diaper here, a mini basin is sinking down into it, but it's still in place. And then it goes on for a ride, like a big boat, several kilometers thick and tens of kilometers transported. The salt just carries it along. Think of the size of these. This could be 40 kilometers wide, just carried by salt. And then what happens is it ends up in another part of the salt sheet and gets stranded there. And if you were to drill a borehole through here, you would hit this unit above the salt and the identical unit below. So you've repeated the stratigraphy. Here's an actual example on the right-hand side. The salt bodies that rose up here. This green unit here of Miocene age is also found above the salt. So identical sediments above and below, just this piece here rafted in on top of the salt sheet before it closed and became welded. So you can appreciate quite a lot of complexity geometrically in 3 dimensions here. So I'm just going to, with this slide, just jump to Mars very, very briefly. We did a study here on a place called Hebe's Chasma, which is a canoe-shaped canyon. It's about 315 kilometers long and 8 kilometers deep. So it's pretty sizable. And we chose it because it is closed in. There's no drainage outlets. So we can rule out the fact that the rivers or any other fluvial processes removed material. But something removed this vast volume of rock there. So in the middle of the Hebe's Chasma is a thing called Hebe's Mensa, which is a flat-topped table mountain there. So that in itself is quite sizable. It's made up of stratified units. And right at the top of the unit is a very mobile stratigraphic layer that has shed a number of flows that have come down the side of it. Well, here's an oblique view. Here's the top of the Mensa, the flat-top mountain inside the chasma. Here's the mobile layer, and these are the 1, 2, 3 flows that emerge from it. Their length is about 17 kilometers, but they do get up to about 70 kilometers. So what are they? Well, Mars is known to have been a wetter planet in the past. That water has gone, so it must have left some salts behind. Mars rovers and orbiting satellites have picked up sulfates, another type of salt, things like kieserite. So that indicates there's a potential for a lot of salt to be involved at the surface. These flows are very, very low gradient, so they were highly mobile. They look a whole lot like salt glaciers on Earth, though I don't think they are pure salt glaciers. What they probably are is a mixture of ice, different types of salts, and various debris, all carried downwards. Those are these little blue ones here that we're looking at blown up in the image here. But all around the side of the chasma are much larger flows there. So end with a bit of fantasy and a nod to William Smith here. What would William Smith have thought of all this? Canal surveyor, fossil collector, stratigrapher, and map maker. Well, he never lived to see the surface of Mars mapped in any sort of detail. But if he had, he would have been very interested in Schiaparelli's map of the Mars so-called canals, published quite a few years later. I'm sure he would have cast a keen eye on the cartography. He might have had something to say about the canal layout there. But I think his chief reaction looking at this would have been, now there is a geological map worth making. Thank you.
We'll indulge ourselves in one question, Martin. Fire away.
Anyone but him.
Oh, what a placeman.
Not with it before. Hi, Martin. What would you say are the two big unanswered questions in the Allochthonous sheet area of salt tectonics? If you were trying to indulge in more fantasy over the next 10 years or 20 years, what do you think we're going to be looking for?
Well, that sounds suspiciously like a planted question. The reason is Chris is working on one of those questions, but I didn't ask him to ask that. One of the big unknowns is, okay, we see on seismic this salt, we see the top clearly defined, usually the base clearly defined, and between them is this fuzzy zone that helps us recognize what salt actually looks like on seismic. But if you go to the field and you look at them, it's not all one fuzzy mess like that. It's intricate layers all folded together and shared and twisted around. And this is a subject that really interests me because it takes me back to the days when I was working on gneisses and other high-grade metamorphic rocks. And so what Chris is doing in our shop at the moment is to use a very good seismic survey that has all these layers revealed in all their hideous complexity. And what we're trying to do is pick them apart and figure out how this pattern got there. So we can actually put some anatomy inside the skin of an Allochthonous sheet. And right now I can't think of another pressing one, but given some thought I probably could.
Well, that's fortunate because we have other pressing matters to press on.